All right, guys, so here it goes. We're tracking. All right, so, we ready? Yes, you can. Okay, Elsie, did you just put those on that stack? Great, okay, thank you. So we're talking about integrated rate laws today. I want to remind you guys, yesterday we talked about integrated rate laws a little bit. What two things do integrated rate laws relate to each other? We learned about this yesterday. Go ahead, Don. Time and concentration, good. So integrated rate laws. Okay, they relate time to concentration. So that's the big concept of today. Okay, so if we want to do the first order rate law integration, the first order integrated rate law. I'm not going to show you guys how the integration is performed because I don't want to scare anybody who hasn't taken calculus, and it's not assessed on the AP test. So that's assessed on your AP Calc test, but not on the AP test, okay? So how we arrive at the integrated rate law is not required information. Just what it actually looks like is required. So the important part, guys, is that you can take a first order rate equation. So what I mean by that would be rate equals K times the concentration of A. Okay, that's first order because there's nothing written here. This is a first order differential rate equation. If you integrate this, okay, and I'll give you just a slight hint to the calc people out there, that would be d of the concentration over d time. Okay, if you take the integral of that, you would end up getting this integrated rate equation, which is ln concentration of A at a specific time is equal to negative kt plus ln A initial. And it's that simple. Okay, so this is what the integrated rate law looks like for a first order rate equation. This indicates the concentration of A at time t, and this is your initial concentration. Okay, that's what that little 0 means. You'll often hear that called not, but it just means your initial concentration. The cool part about these is that they follow the y equals mx plus p format. So this looks really messy and kind of random if you're not used to seeing integrals, but it actually, if you see it correlated with y equals mx plus b, it looks really pretty easy to digest. So I'll show you that. Okay, so that's the integrated, and then if I identify this, this would be our y, this would be the m, this is x, and this is b. Okay, so you guys can kind of see how that connects into the y equals mx plus b format. Okay, so here's the cool part. If you want to figure out what type of reaction is, so if you have data and you don't know if it's first or second or 0 order, what you can do is graph it in a number of different ways. And if the graph of ln versus L of your concentration versus time is linear, then you know that it's a first order equation. If it's not linear, if it ends up being a curve, it's not first order. Okay, so if you have this versus time, it's going to be linear, and that's your first order equation. Okay, Something to take note of for first order equations especially is that your slope is equal to negative k. So when you set it up like that, if you do graph it, the slope of that linear line that you're going to get is equal to the negative k. So this is handy if you just have data and you need to figure out what your k is. You can graph it and then find the slope, and then you can get your k. There's lots of stuff you can do with that. Other forms that you might see of this same equation. So we can manipulate this around to solve for different things. So one form that you might see is ln of A initial over ln of A at a specified time is equal to kt. That's one version you might see. Notice that we have a positive k now. And one other version that you might see is the concentration of A at a given time is equal to the initial concentration times e to the power of negative kt. So that's another way you can look at it. So if you're familiar with logarithms, these manipulations kind of look familiar, but if not, just memorize them. Okay? So there's that. Any questions so far? I know these really don't make sense until we start to actually use them, so that's why I have some example problems for you guys. So here they go. I would include these in your notes. Okay, so what I want you guys to notice, the first thing that we've got on this paper, do you guys notice how we have a graph and a table? And if you notice, we've got time as one column on the table, and then the natural log of the concentration of a reactant on the other side of the table. And if you guys notice, is that graph linear? It is. So that would be definitive proof that this is a first order equation. Okay, so if you see a graph and you have the natural log of concentration on y, time on the x, and it's linear, bingo, you're first order. Okay, go ahead, Lynn. Lynn. Aline, I'm sorry. Go ahead.
Okay. For zero order, is it like a non-existent graph?
No, it would still be a graph, but if you graph the natural log, it wouldn't be linear. Yeah, we're going to talk about that later, what graph would give you a linear thing for a zero order. Okay, so let's take a look at what this question's asking us to do. So for part A, it's asking us to write the integrated rate law. So guys, what is the reactant in this reaction? N2O5, yeah, that's given to you in the problem. So the reactant is N2O5. So we're going to plug this in to our integrated rate law. And really, we're just going to substitute A with our reactant. So if for number 1A, the integrated rate law then would be ln N2O5 at a specified time is equal to negative Kt plus ln concentration of N2O5 initial. Okay, so that's what the integrated rate law would look like for this problem. Okay, simple enough. Next up, it's asking us to calculate the rate constant K. So if we want to find the rate constant K, what about the graph do we want to find? The slope, yes, because remember guys, the slope of this line is equal to negative K. So if we can find the slope, we'll have K. All right, how do we find slope? What's slope? Change in yeah, so slope is equal to delta y over delta x. Raise your hand if that looks slightly familiar or somewhat familiar. Hopefully, oh my gosh, please all raise your hands. Okay, all right, so in that case, I'm just going to take 2 data points from our table as my y and my x. So what column is y? The ln column, and you guys are looking at me like I'm done, but really, I want to know that you know this. And then time is x, right? So I've always seen people use the first and last coordinates, so I'm just going to stick with that. I'm sure if you use not the first and last, you'll have the same slope because it's linear, but I always just use the first and last. So in that case, then my last point, the y value for my last point is negative 5.075, and I'm going to subtract that from my first point, from that to 303. Okay, do you guys see where I'm getting these values? This is the last ln concentration. This is the first ln concentration. Okay, and then my last time was 400 seconds, and my first time was 0 seconds. Okay, so when I do that, I can calculate that out, and that's going to get me negative 6.63, nope, 6.93 times 10 to the negative third. Now here's the question. What are the units going to be on this? Seconds to the negative 1. How did you know that?
Order of reaction.
Yes, this is a first order reaction. So just like we talked about yesterday for units on K, first order reactions have a unit of seconds minus 1. Okay? So it's that simple. All right, so now we have our K. Have I lost anyone yet? No? There's something that I have to do really quick. Is this actually my K, or is it? It's my what? It's my negative K, right? So the slope is negative K, so then the K value itself will just be the positive 6.93 times 10 to the negative third. So S minus 1. Now I've got the K. Okay, so keep in mind, guys, that for first order reactions, the slope is negative K. You just have to reverse the sign. Okay, so that was number 1, A and B. Questions so far? I want to make sure I'm not going too fast. Okay, and then on for number 2. So now that we have our K, we can calculate what the concentration is after 150 seconds have happened. So that's what we're going to do for number 2. So we have to use the integrated rate law to do this. So for number 2, the question is asking, at 150 seconds, what is the concentration? So this is how I'm going to set it up. Negative K T plus ln of N2O5 initial. Okay, so I am looking for 150 seconds, so this is what I'm solving for, so that's not going to change. N2O5, 150 seconds. But I can plug my K in, so my negative K is 6.93 times 10 to the negative third, S minus 1. It's asking for 150 seconds, and I'm going to add that to the natural log of my initial concentration, which is, it tells us in number 2 that the initial concentration is 0.100 molar. All right, so I feel like I'm talking too quickly. I'll slow down. So do you guys see what I did there? I just plugged in the time of 150 seconds. I plugged in my K, and I plugged in my initial concentration. Okay? And we're solving for the concentration at 150 seconds. Okay? Okay, so now I can do all this math out, and once I do all that math out, I end up getting negative 3.343, and that's equal to the natural log of N2O5 at 150 seconds. Bonus question, who knows how to get rid of natural logs? What do you do? E to the power of. Good. So we're going to take now to get rid of this natural log, because we want just this answer. We want to get rid of the natural log part. You do e to the power of both sides. Okay? And once you do that, you'll end up having the concentration of N2O5 at 150 seconds is equal to 0.0353 molar. And now we're done. Yes?
I don't get where you get all these LN.
It's because, and this is not required knowledge, but it's because the integral of 1 over x is natural log of x. Does that sound familiar?
Yeah.
Yes. And so when I'm going to send a YouTube video out for those of you who are interested in watching. You could find the derivations online just to see how they actually arrived at.
What are we deriving?
You're deriving delta A over delta T equals K delta A. That's what you're deriving.
Oh.
Yeah. Okay. Okay. All right, a note about sig figs, guys. For natural logs, the number of sig figs when you're dealing with natural logs is the number of decimal places in the exponent. Okay, so how did I say that? Sig figs are in E. And I had a reason for this, and it has escaped my mind for the moment. And I'll try and remember it during the break. And I'll tell you guys if I remember. But anyway, so that's why we have 3 sig figs here. There was 3 decimal places in that. Okay? All right, so that was number 2. How are we feeling so far? Good? It's really just plug and chug. A lot of people get scared when they see all these numbers and stuff, but really it's just plug and chug. Okay, so let's take a look at number 3. Once you guys have that copied, flip over to the back of your page. All right, so we have a new set of data. We have a new reaction, and it's asking us a few questions. So the first question, determine the differential rate law. So this is going to look a lot like the stuff that we did yesterday. Do you guys notice how we have 3 different trials, and we have 3 different rates and 3 different starting concentrations? So we're going to do exactly what we did yesterday in order to figure out the order of this reaction. So I want to remind you guys that you can't just dump everything we learned yesterday and start new here. We have to kind of fold it in. So we're going to start with that. So what I did to do this one, I took trial 2 over trial 3 to figure out the order. So I'm just going to do everything that we did yesterday. So 7.2 times 10 to the negative 3 molar per second. That's the rate from trial 2. Divided by the rate from trial 3, 2.4 times 10 to the negative 3rd molar per second is equal to, and then my concentrations, 4 to the n, 1, 8 to the n. The reason I'm doing this, guys, is because the rate law for this equation, the differential rate law, is going to be pH3 to the n power, and I'm trying to figure out what the n is. I realize I just wrote a million things on the board, so I'll pause. Yep, any trials, because there's not 2 reactants in this case. Okay, and again, this is all stuff that we did yesterday. So when I do this math out, this divided by this ends up being 3. And this divided by this ends up being 3 to the n power. So what must n be then? What is it? 1. Hey, look over here. I swear, I feel bad for these YouTube people because they get blank board for like half the class. Okay, so n is 1, so that means we must be a first order reaction. Okay, so now we figured out A. And as far as B goes, okay, so for B, now it's asking us to find the K. So we know how to find K. We're just going to plug in information from the trials into our rate law. So I'm just going to do that. So for B, what trial did I use? I think I used trial 2. So my rate was 7.2 times 10 to the negative 3rd molar per second was equal to K, times the concentration at that trial was 54 molar. And so now my K is equal to 0.0133. And that's, what are my units for my K? S to the minus 1, because this is first order, and the units on K for first order are S minus 1. Okay, now we get to dive into the new fun stuff. Now we're going to write the integrated rate law, which you guys have seen one example of, and I want you to do it now. So please write the integrated rate law for letter C. Okay, Sabrina, help me out. What's my integrated rate law? Mm-hmm. Oh, you didn't do the rest yet? Okay, who can finish it off? Micah, help me out. pH3 with a little 0. That's a not sign, meaning like original or initial. Okay? All right, so this is our integrated rate law. Raise your hand if you wrote something similar to this. Fantastic. Okay, and for the last part, letter D, it's now asking us to figure out what the concentration of pH3 would be at 360 seconds. So because we already did one example problem, I want you guys to do this. And I want you to use the information from trial 1, okay? Because your initial concentration changes for each trial. So use trial 1 to do part D, okay? And if you need help, look back at the last problem that we did because it's the same idea.
In my mind, when I hear my voice, like, yeah, it doesn't sound like pitch.
Okay, guys, so this is how I set it up. Once I get it set up this far, then I can solve for this side of the equation. And then take e to the both sides. Okay, and then my concentration of pH3 will be 0.00900 moles. Raise your hand if you got an answer somewhat close to that, or that at least. Yes? Good? You wish math was this easy. This is applied math. I hate crunching numbers for the sake of crunching numbers, but this has a purpose. Okay, so you could have done it that way, or there's another way you could have done it. Do you guys remember this form of the equation that I showed you? Okay? You can plug it into that form of the equation, and it kind of simplifies it down to one step. Anyone can do this with me if you guys want to see if I'm wrong. Okay, second E equals negative 0.03 times 360 times 1.08. Okay, yeah, that gets you 0.00899, which is essentially the same answer. Okay, so cool, both ways work. If you guys want to do either way, that is fine. I'm the kind of person who does everything the same way every time because I'm a really methodical person. So if you want to just stick to the first way you learned it, that's fine. Or you can learn this way. Yeah?
Can you show us how to get that LM equation?
I'll send the YouTube video out because it's kind of long and it's going to scare people who haven't taken calculus. So, but I'll send it to you though, for sure. I'll mass text it out. Okay. So that was D. Let's see, where are we at on this worksheet? So we have done that one. All right, number 4, half-life. I have to pause real quick and give you guys some notes on half-life. So here it is. Yes? Oh, you didn't have to. You could have used any of the trials. What is the rate for trial 1? 0.199. It's 0.0129. They will vary like that because of rounding errors for each value, but they're going to be close enough that you could still use them. But yeah, I hear what you're saying, and actually if you do it for every single one, you're going to get a slightly different answer every time. But it's unavoidable. It happens. It happens. So as long as you're close, that's okay. Okay, so half-life for first-order reactions. Okay, to understand what half-life is in the first place, we got to know the definition. So the half-life, guys, is the time it takes for a reactant to reach half its original concentration. So pretty straightforward. So time required for a reactant to reach half of its original concentration. To kind of elucidate this idea, I want to show you, so let's pretend this is like a pie graph representing how much of your reactant that you have. So this is 100% concentration. Okay, so after one half-life, your concentration will be halved, right? Because that's a half-life, okay? Now, guys, after your second half-life, how much is going to be left of your total initial? A quarter, right? Because half of this will be used. Okay? See you later. So before I let you go for break, just keep in mind that if you want to reach 75% of your original concentration has disappeared, it only takes 2 half-lives, okay? And then after your third half-life, only half of that disappears. And after the fourth half-life, half of that disappears, and the fifth, half of that disappears, so on and so forth. So it's very hard to actually eliminate everything of a certain reactant because it just slows down its elimination rate. Okay? All right, go ahead and take your break. Yeah.
Are we supposed to do the